Hi, my name is Prakash Gupta, and this is my LAB1 video report for Physics 2211. So let's jump in. For introduction, we had one main goal, to describe the motion of an object traveling with constant velocity in one dimension using a variety of tools and principles, and to compare the efficiency of our methods here. So in instructions, we were to take the video of an object moving in a single direction and use the tracker software to analyze this video and extract the position. Then we were to develop a computational model for the system and compare the results from these two. The principles here are Newton's laws of motion and the velocity and position update equations. These allow us to create those computational models and to create motion with constant velocity. Our results showed that the experimental data was consistent with the computational model, implying that the design did match these principles. So let's look at that design. To obtain our video, we manufactured the required motion by rolling a spool of twine across a lab bench in front of a meter stick. Our system here is the roll of twine, and our surroundings are the table and at large the room. So why? By Newton's second law, an object in motion remains so unaltered when no net forces are acting on it. So to obtain that constant velocity, we needed to apply a force and then ensure that no forces, or in total, no forces were being applied throughout the duration of an experiment. We also knew it was important to choose the x direction as opposed to the y, because gravity will act if something's falling in the y direction. Here, it's not falling, so we didn't have that issue. The meter stick is used as that's necessary for tracker, as is the phone placement. Let's watch that video. We know from our video that the experiment lasted 3 seconds and that the total distance traveled was 26 centimeters. From here, we can use Newton's laws and the velocity and position update equations to build our predictive model and simulation. And we can do that by defining our initial conditions. As we know, the roll started at the origin and started with an initial velocity of the distance over the elapsed time, as the average velocity is equal to the velocity in a constant velocity system. I just said velocity several times. We're going to use a time step of 0.03 seconds to match the frame rate of our video for convenience and data analysis. Then, in looping, we're going to apply the position and velocity update equations. Here, we're working with constant velocity, so we're going to update our velocity by 0 each time. And that's consistent with what we said about Newton's law, because if we look at the velocity update equation, if we have 0 force and our object remains in motion unaltered, then the additional term in our velocity update equation will become 0, as F net is 0. From our position update equation, we add the v average, which is equal to the constant velocity, weighted by the time at each step. Finally, we're going to print that data out so we can review it and graph it elsewhere. Here we can see the code, which matches all the things that I've just said out loud, and the sample graph that was resulted from our closed script code. In terms of data analysis, we needed to analyze our video now. So we uploaded that to Tracker, to a physics software, which extrapolated a position to time relationship, and we retrieved that data in CSV format. The data from our computational model was, we said, printed out, and we retrieved that as well. We can reconcile this into a combined line graph in Excel and compare the two results and see how well they fit. So here is that graph. We can see the tracker data, which is in blue, is slightly more erratic, and our simulated data is perfectly linear, which matches because any discrepancies we would have would appear in that real world. So let's see. From this, we can see that they're actually fitting really well, which means that this was a good design and that it fit the principles measured or desired. So let's discuss that in a little bit more depth. So because the models matched so well and our computational model was built entirely upon the physics principles and Newton's laws, our system and our experimental design also matched that. So we did succeed in producing constant motion under no net force. Regarding the discrepancies in the data that we saw, technically, rolling it is different from translational motion. And additionally, more importantly, the tracker software and our use of it is not perfect. So any discrepancies might have arose through that. regarding the main questions, which are how would our results change if the axis was flipped, we could consider the origin to remain the same, but all of our travel to be in the negative x direction, which would result in a reflection of our graph over the x-axis. And basically, our lines would both be pointing down. We would do this in both models, meaning we'd maintain consistency. And what does it mean? Is it possible to say how many pushes we had? No, because net force is a sum, and we don't know what the forces are, just that their sum was 0. Thank you.